Hello and welcome to another episode of the Hydrocarbon Engineering Podcast. I'm your host, Callum O'Reilly, and today we're bringing you a special episode where we talk to a number of experts about the economics of e-fuels. As the marine, automotive, and aviation industries aim to reduce their carbon footprint, understanding e-fuel cost structure is essential for all stakeholders. Joining us to provide a clear analysis of the factors influencing e-fuel pricing, as well as the economic challenges and strategies for cost reduction, are Skoufa, Managing Director, Methanol at Johnson Matthey, Tommy Wind, Senior Future Fuels Manager at Maersk, Leigh Abrams, Senior Business Leader for Emerging Renewable Fuels at Honeywell, Clara Bowman, COO of HIF Global, and Lawrence Navin, Vice President of External Affairs at the Methanol Institute. This episode is an excerpt from a recent Insight seminar that Hydrocarbon Engineering had the pleasure of hosting. I'll be back at the end of the episode to provide a little more information about that seminar and how you can access it. But for now, let's turn to our panel of experts to get their thoughts on the economics of e-fuels.
The Hydrocarbon Engineering Podcast is brought to you by Owens Corning Foam Glass Insulation. From managing vapor drive and mitigating corrosion risk to maintaining thermal performance and supporting safety on the job site, the insulating system plays a critical role in high-performing hydrocarbon processing facilities. Learn more about how foam glass insulation contributes to the design of high-performing insulating systems at cryogenic facilities at www.owenscorning.com/foamglasslng study. That's www.owenscorning.com/FOAMGLASLNG study.
So a warm welcome to our panel. Now, I thought it would be useful to begin our discussion today with an introduction to e-fuels. So I'm going to turn to you first, Zina. Please, could you provide us with an overview of the role that e-fuels will play as a solution for hard-to-abate sectors such as aviation, the automotive industry, and shipping?
Thanks, Callum. Certainly, e-fuels are produced using renewable electricity, water, and captured CO2. When the hydrogen that is used as a feedstock and from water electrolysis is produced using low-emission renewable electricity, and when any carbon inputs, so the CO2 that we are sourcing, the carbon dioxide, is obtained in a way that leads to low life cycle greenhouse gas emissions, then e-fuels are considered low-emission fuels. And so e-fuels made from biogenic or captured CO2 directly from the air, they can then provide potentially full emissions reduction leading to what is called carbon neutral fuels. There's a plethora of different LCA life cycle analysis studies out there. We've done our own LCA analysis, which shows significant reduction of greenhouse gas emissions using an e-fuel pathway. E-fuels are a key solution in decarbonizing the transport sectors, but particularly, as you mentioned, those hard-to-abate sectors which cannot be electrified, such as the marine and aviation sectors. And they can also provide an option for a multi-technology pathway to reduce emissions in the automotive sectors. Specifically, if we talk about aviation and automotive sectors, e-fuel can be drop-in alternatives without requiring major infrastructure change, enabling a quick market entry while using existing transport, existing storage, distribution infrastructure, and the end-use equipment as well. For shipping, e-fuels such as methanol can be easily bunkered. Methanol is already a commodity that's transported around the world. And for example, methanol engines can be retrofitted easily into existing vessels. There's also development of new vessels powered by methanol already. And this potential of e-fuels is already recognized by policy makers. They see the potential of e-fuels due to their high carbon abatement potential. For example, the European Union has introduced a number of measures to incentivize the use of e-fuels. Going the longest way is the Refuel EU Aviation, which includes specific sub-mandates for power to liquids all the way until 2050. RED III transport, Fuel EU Maritime also have RFNBO targets in place. So e-fuels, renewable fuels of non-biological origin targets. And also here in the UK, the Sustainable Aviation Fuel mandate includes an increasing power to liquid sub-mandate en route to net zero.
Great. Thank you very much for that detailed introduction, Zina. So how do e-fuels compare to biofuels? Leigh, maybe you can help us out with this one. And how do they match up when it comes to efficiency and scalability?
Yeah, I'll focus my answer in particular on the aviation market, because as Zina says, that's one of the hardest to abate sectors and one of the critical ones where we have established biofuel pathways today for the production of sustainable aviation fuel. Honeywell has technologies in that space, and so we have a fairly good view as to the cost of production. And today, biofuels are cheaper than e-fuels. But I think that's today. When we look to the future and we look to scaling up to meet those targets and mandates that have been put in place by global policy, we'll get to a point where these e-fuels are not only necessary to meet that demand, but also as green hydrogen matures, as technology space and renewable energy costs go down, you'll start to see more cost competitiveness. Because the big difference between bio and e-fuels is the availability of feedstock. We cannot achieve all of the targets for decarbonization with triglycerides or ethanol feedstocks alone. And that's really why something like e-fuels is a key enabler to targeting sort of that global mandate level of fuel adoption. Generally, what we see is in a biofuel project, your costs are really driven by your feedstock cost. I think as e-fuels become more prevalent and are used in abundance, what we're going to see is that's going to shift a little bit to a bit more focus on the CapEx required to build these projects initially. But in the long run, we're going to source much lower cost and more abundant feedstocks, CO2, renewable energy, that are going to enable those fuels to be competitive.
Okay, thanks for that, Leigh. And I wanted to just pick up on something that you mentioned there. So in terms of e-fuel production, how available is renewable electricity and how accessible is CO2 today? And where do you think that it's going to go?
I think you're, hit the nail on the head there. Availability of feedstock is quite key and for e-fuels deployment. And on that end, let's start again. What do we need? We need availability of renewable electricity and we need availability of the right source of CO2. So starting from renewable electricity, I would say that location of the project is key. We need to find those locations that have abundance in renewable electricity, that also make sure that there is a high capacity factor for those renewable power sources, solar, wind, for example. So this is a key. Equally, location plays a critical role when it comes to availability of the carbon dioxide feedstock. And this CO2 feedstock sourcing at competitive price could be a potential issue in the market at some point, depending on the region. We should, for example, take into account that if we're looking at developing a project looking to offer e-fuels for the EU market, where the RFNBO regulation is what governs this market, then this regulation requires certain types of CO2 to be used as the feedstock for e-fuels in different points in time. So this has to be taken into account. Another consideration is locking in longer-term certainty for carbon dioxide feedstock supply in regions like Europe, for example, may likely raise costs today, or the expectations that price for carbon dioxide sources will increase in the future. Again, as we said, the EU regulation gives the availability, the option of using some fossil CO2 sources up to a certain point in time, 2035, and then 2040, there's another milestone there. But then we should be also taking into account that the right fossil resources to be used within that time frame are also quite, so it's quite then important to consider the role of direct air capture, because that can unlock the availability of eligible carbon dioxide for the production of e-fuels. And biogenic CO2 is also very important. At some points, as the available, high quality, easily accessible biogenic carbon dioxide sources are limited, because we start building those plants and using those sources up, then the cost of biogenic CO2 and direct air capture will potentially start to converge, because right now direct air capture is at a high cost level. So location is key, and the successful projects that we have seen going forward are those that are built at locations where we have abundance of renewable electricity and you have the right CO2 source available.
Great, thank you for that, Zina. So location, but I heard the word cost a few times there as well. So I wanted to move on to the cost components of e-fuels now, which are obviously vital. So Clara, are you able to guide us through some of these key cost drivers? And what do you think can be done to bring the cost down?
Sure. Well, when you take renewable energy, you put it in an electrolyzer and you make hydrogen, you then combine that with carbon and you have your fuel on the other side. And so each of those are the key cost components of the e-fuel, as Zina was saying. If we look at renewable energy, that was coming down for many years, almost continuously. There was a bump after COVID where renewable energy prices started to go up again. We're now seeing them coming back down. And that's great news, because that's about 60% of the cost of your e-fuels is related directly to your energy costs. So places where you can have really cheap and competitive renewable energy, you'll drastically reduce the cost of your e-fuels. The next step, which is super important, is the electrolyzer. From there, again, we're seeing reduction in costs and also increase in efficiency. The reduction in costs is due to having better construction strategies. So looking at larger units where you're able to optimize more, have less equipment. And then the increased efficiency is coming from some technological breakthroughs, some of which aren't completely proven yet. They're not quite ready for prime time, but they're coming, such as the SOIC electrolyzers, others just improvements on the technology that's available today. That has a huge impact. If you think, for example, about going from a regular electrolyzer to a SOIC electrolyzer, it means using 13 megawatt hours of energy to make a kilo of hydrogen, going down to somewhere between 7 to 8. So really drastically decreases your overall cost of fuel. And then we come to carbon capture. And with carbon capture, what we really need to see, we think, is a scale up of the technology. Again, driving more investment, technological improvements that'll allow us to be more efficient, use less energy in the carbon capture, and also more efficient in the capture of the carbon itself. Those are all technical things that can be done to drive down the cost. There are a few things that can be done on the regulatory side that would drastically decrease our costs that really don't require anything else other than a sense of the reality of the situation that we're in right now. What we're seeing with a lot of regulation is that they're kind of imagining the world that they would like us to be in 2050 and imagining it that we're there now. And so that's causing a lot of very specific, very tight regulation, which just drives up our cost. So the example that Zina gave of industrial CO2 is a great example. You're allowed to use industrial CO2 within Europe, but basically any CO2 outside of Europe doesn't meet that very exacting regulation that we have. And so we can only use biogenic CO2 if we want to qualify to be able to do an RFNBO import into Europe. So that just drives up cost. If you're paying another $100 per ton of CO2, that's $140 per ton of methanol difference. So it really makes a difference in your cost. The other area is in the requirements around sourcing of electrical energy. So the tighter your matching is, if you have hourly matching where you have to hour for hour match your facility, that also drives up your cost. And I think probably unjustifiably, we've done some studies in the case of Texas that if we just had 80% hourly matching, we would have an equally good impact on reducing the overall energy intensity of the grid and a much lower cost overall for our e-fuels. So thinking about some flexibility in the regulations as we move forward is a very sensible way for us to be able to meet our obligations, get these projects off the ground, do something that's really good for the environment, but not at a cost that can be prohibitive.
Really interesting. Thank you for that. So, Lawrence, I wanted to bring you in now with an important question given geopolitical events at the start of this year. So what policies and market dynamics are affecting e-fuel pricing, and what are their implications on the market?
Thanks, Callum. Living in a time suddenly of what appears to be rapid change in the global political and economic order, I think it's unclear overall how much these events will influence e-pricing and uptake. But at the Methanol Institute, we generally remain very upbeat about the prospects of e-fuels. There's several policies and market dynamics that impact the pricing of e-fuels. I think Zina and Clara have covered a lot of them: renewable energy costs, feedstock availability and costs, technological advancements. I'll focus a little bit more here maybe on some of the regulatory drivers, such as carbon pricing mechanisms, policies like the European Union's emissions trading system that aim to reduce greenhouse gas emissions by assigning costs to carbon emissions. So while renewable fuels may not currently be as inexpensive as fossil fuels, the implementation of carbon pricing is expected to increase the cost of fossil fuels and potentially making renewable and alternatives more competitive. And that's something that will only accelerate over time. I think other areas beyond the EU where we can look at this of particular importance is what's going to happen at the International Maritime Organization's Marine Environment Protection Committee meeting that's coming up in April, where we may see a carbon pricing mechanism brought forward that would have global implications there. And then additionally, within the US market, we have, I think Clara alluded to some of this, the Inflation Reduction Act and tax provisions there that exist, such as 45V, which is for clean hydrogen production, and 45Z, which is clean fuel production tax credit, for which in the initial guidelines, methanol would qualify. And there's been a reference in those guidelines as well to use of methanol as a marine fuel. I think these are really positive developments. The Methanol Institute just recently submitted a response to the U.S. Department of Energy as they seek to create a definition for sustainable maritime fuel. And, as we see all these carbon pricing mechanisms come to bear, and we've just surpassed now 1,000 either methanol dual fuel or methanol ready vessels in global order books. These ships are coming and we need the fuels for them. And so the regulators need to keep up with that, recognizing that reality. And I do think we're off to a good start.
Great. Thank you for that, Lawrence. So a lot of talk about policy. And I was wondering, Clara, if I come back to you, so do global policies need to do more to support the scale up of e-fuels?
I think we need two things from global policy. One is consistency. So I'll give you an example. The e-fuel mandate for eSAF in Europe, there are a lot of people speculating about whether that will get delayed or changed. It's really important for us to know that the goalposts are there, we're all moving towards it, and that there's going to be an objective that everyone is going to have to apply to or move forward with as we go forward. Because if we don't have that, then people are just not able, first movers are not able to take the decisions that they need to be able to commit to these long-term projects. And we really need to be able to get an e-fuels project off the ground. Long-term offtake, we're talking 15 years ideally, because it's all CapEx up the front and we need to have a lot of certainty of cash flow throughout the project. Other regulatory amendments that would be helpful in the EU, for example, is grandfathering, recognizing that when we take FID and we start to build the project, we need that same set of regulations to apply for the life of the project. We can't get 5 years into our project and find out that the rules have changed and all of a sudden we don't have RFNBO anymore. We have, nothing. And we're selling on the fossil market. So these are the sorts of things that when we talk to banks, that the questions that they're asking us, and we need to have really strong answers as we go into the financing mode for these projects. If we have that consistency and the realism with some of the elements that I spoke about earlier, which allows us to produce the same fuels, same environmental quality at a lower price, then I think the e-fuels sector will be able to expand very quickly.
Great. Thank you very much, Clara. So Leigh and Tommy, I wanted to pick your brains on some of the economic challenges and opportunities that e-fuels present. So what do you consider to be the main barriers to e-fuels adoption, and perhaps what can be done to overcome them?
Yeah, we have already heard a lot of good input on the challenges. To repeat, I think from a project development perspective, some of the challenges are related to the high capex, typically for these types of e-fuel plants, the relatively high electricity consumption, given that all the energy input to e-fuels basically comes from electricity. Whereas if you produce biofuels, part or all of the energy content of the products will originate from the biomass. So there's a lot of electricity required. And as we also heard, competition and availability of low-cost renewable electricity is often a challenge. So if your plant is to be located in a populated area, such as the EU region, as an example, the consumption of electricity will be in competition with other sectors, electricity consumption in society as a whole. And this drives up the effective power price. So those are some of the challenges that we see. But going to the opportunities, there is also a number of things to mention. For example, you could also look for plant locations where it's less populated. So if you move to, for example, the Middle East or other places, you will often end up with electricity production that is more what I call island mode, where you cannot necessarily connect directly to the grid. And this means that the effective electricity price for such a project will get much closer to the levelized cost of electricity, since you are not in competition with a lot of other consumers. And finally, I will mention, if you are in a region, on the contrary, where you're connected to the grid, then of course you can try to harvest the low electricity prices when there are peak production from wind and solar, for example. The challenge is just that those hours during the year may be limited, where you consider really cheap prices. And the final thing I will mention on the opportunity side is that from Maersk side, we see that e-fuel can offer really good well-to-wake carbon intensity reductions. So e-fuels have very low to-wake emissions, as we also heard Sina mentioned, and they typically perform better than both their biofuels.
From my side, I think Tommy's exactly right, and he's pointing out a lot of the things that I would point out as well, which is that if you can identify that low-cost place for production, that's oftentimes a critical factor in these projects. And when we talk about methanol as the linchpin of e-fuels projects, I think the key enabler there, again, when I'm looking at something like SAF production for European markets, is you don't necessarily have to produce your SAF at the same place that you produce your methanol. And that really enables you to simplify the Venn diagram of, do I have biogenic CO2 source? Do I have low-cost renewable energy? Do I have a facility that can host that sustainable aviation fuel production? There's fewer variables that have to be true in a single place when you can think about methanol as a fungible and shippable intermediate. And that's really going to help with the overall economics of the project. The other point I would make is just to reiterate what Clara said, which is that credits that are long duration and certain are ones that make projects bankable and allow them to achieve financial close. Without that certainty in regulation, these become really challenging to move forward.
Great. Thank you both for your thoughts on that. Lawrence, in light of what Tommy and Leigh have said, if you could change one thing today to support the adoption of e-fuels, what would it be?
Thanks, Callum. Yeah, I think this has been mentioned just now by Leigh, a component of this, and earlier by Clara as well. It's the consistency of regulations, the certainty of duration of credits, the harmonization of international regulations. I think nested within all that, one very important thing would be the widespread implementation of full life cycle analysis of these fuels. So using LCA as a standardized method to assess the environmental performance of all energy carriers would be an important step. It ensures that emissions are evaluated across the entire value chain, promoting a level playing field among different fuel types, and encourages the adoption of low carbon alternatives like e-fuels. By promoting the kind of policies that mandate LCA for all fuels, and, say, particularly from a marine perspective, this would be a full well-to-wake version of a life cycle analysis. By promoting these policies, stakeholders can make informed decisions, and they would have access to comprehensive environmental impact data. This facilitates the recognition of the true benefits of e-fuels, such as e-methanol, that can reduce greenhouse gas emissions. And I think that Tommy talked about this. E-methanol can reduce greenhouse gas emissions by up to 95% compared to conventional fuels. So this would all be a very important step to take, and we'd see the true benefits of these fuels.
Lawrence, if you don't mind, I'd love to just add one thing to that, which is that in the biofuels market, we see that when you incentivize carbon intensity and driving to the lowest carbon intensity, you end up with economic incentives for efficiency. I think is really valuable in this space too. Right now, there's a key threshold, and if you reach that threshold, you don't get paid anymore for additional carbon intensity reduction. And what you're talking about is, let's put a mechanism in place for that to be feasible.
Yeah, absolutely.
Very interesting. Thank you both for that. So what do you consider to be the biggest threat to establishing an e-fuels market at scale that will really make a difference to global emissions?
I think we have people who want to do e-fuels projects. We have people who want to finance e-fuels projects. We have people who want to buy e-fuels. And their concern is that by buying e-fuels, they're going to be out of the market, or they're going to be uncompetitive as compared to their peers, and they're going to fail as a business because they can't take on these kinds of responsibilities. And so to me, the biggest threat that we have is a signal that we no longer care about climate change. It's all too hard, it's all too expensive, and we just want to give up. And that signal is going to be very, very dangerous to people like Maersk who are trying to do the right thing, trying to get out there and buy these long-term contracts for e-fuel. I think that we've seen a world with a lot of inflation. We've seen a world with war. People are kind of reassessing their priorities and perhaps getting a little bit frustrated as well, because there were a lot of very big goals that were put out saying that we're going to do these huge things by 2030. And all of a sudden it looks like we're not going to be doing those things. And so I think there's a collective kind of stepping back and saying, oh, what are we doing here? And so what we need to do is to focus on realistic targets that are achievable and stick to them. And if we do that, I think that there's enough people who are really dedicated to make this happen, and we will do it, and it will happen even faster than what we think. But we really need to have that consistent vision that maybe things might change around the margins, but the overall direction that we're going in is that there will be a price on carbon. We are decarbonizing. We might do it in a way that is progressive and sensitive to the other requirements that and budgets that people have. But decarbonization is an important part of that, and we're going to be moving forward with that. And I think that is a consensus that is shared around the world. But I would say that's the major threat that we have. If we want to decarbonize in a major way, e-fuels will definitely be a part of that.
That's all for today's episode. I'd like to offer my thanks to our panel for their expert insight into the cost components of e-fuels, market dynamics and current trends affecting e-fuel pricing, and some of the economic challenges and opportunities. As I mentioned, this episode was an excerpt from a recent insight seminar that Hydrocarbon Engineering hosted with Johnson Matthey. If you'd like to watch and listen to our entire conversation, which dives into recommendations to manage and reduce costs and considers the future outlook for the e-fuels market, you can do so for free. Simply head over to hydrocarbonengineering.com/webinars and search for this online seminar, which is titled Traveling Towards Sustainability, Exploring the Economics of E-Fuels. Thank you for listening to this episode of the Hydrocarbon Engineering Podcast. Please like and subscribe if you enjoyed this episode, and join us again soon for more conversations with industry experts.
The Hydrocarbon Engineering Podcast is brought to you by Owens Corning Foam Glass Insulation. From managing vapor drive and mitigating corrosion risk, to maintaining thermal performance and supporting safety on the job site, the insulating system plays a critical role in high-performing hydrocarbon processing facilities. Learn more about how foam glass insulation contributes to the design of high-performing insulating systems at cryogenic facilities at www.owenscorning.com/foamglasslng study. That's www.owenscorning.com/FOAMGLASLNG study.